So what is definite integral? A definite integral is an integral to be evaluated between a lower limit a and the upper limit b. Now, what is lower limit a, upper limit? We'll see. Okay, a definite integral has a unique value. So instead of, because indefinite integrals, we are ending up with an arbitrary constant. Remember that c we don't know. That c can be anything. That c can be 1, 2, 3 infinite values. That's why we'll not understand the complete value of the integral. But in case of definite integral, that c will be cancelled out when we use the limit. So we'll have a unique value. That's the meaning of this statement. A definite integral is denoted by integral of, whenever you have a numbers like this, that means it is the limit. And what is that a and b indicating is the value of x from a to b. Okay. For example, if I have an integral of f of x, a to b, let a be 1 and b be 2. And let me explain this function as x square, which is a parabolic function. And the value of x is 1 to 2. So what is it suggesting is, this is a parabola with the axis y-axis, and x is equal to 1 here, x is equal to 2 here. So if I want to find the area under this function between x and y, 1 and 2, what is the area? This is what the meaning of this is. So when we integrate this, we get x cube divided by 3 starting from 1 to 2. That means my problem becomes x cube by 3, substituting x as that is 1 to 2, which will be 1 cube by 3 plus c minus 2 cube by 3 plus c, which will be completely subtracted, and modulus value. We already set the positive value, so c will be cancelled. So we end up with 1 by 3 minus 8 by 3 mod of that, which is simply 7 by 3. This is a quantity which is a definite value. That's why it's called definite integral. So it depends upon the curve. So here, this example I gave is a parabola, and there's a random curve here, and we're talking about indefinite integral comparison, the definite integral comparison. So indefinite integrals, we don't know where it is ending. The area keeps on going until as the curve keeps extending. Okay, whereas in the definite integrals, the curve can be anything, but we are only looking at the definite area between the two limits, x is equal to a and x is equal to b. Okay, so this is nothing but understanding the area of the area of a region below the curve within the given limit, because an indefinite curve can be, for example, the same parabola can be extending to indefinite range, right? As it is extending to infinity, I won't be able to understand the exact value of the area because I don't know the limit. But when I give a limit, it becomes a very definite value. That's why it's called definite integral. Hope this part is clear. Yes. Now let's go to the next one. Let's solve some example. Yes. Let's go to the next part of this. There is a very important theorem called fundamental theorem of calculus. So what is this theorem says? Mathematically, the definite integral is often computed using an anti-derivatives of the function. Okay. So fundamental theorem of the calculus states that if f of x is an anti-derivative of the f of x, then integral of a to b f of x dx can be written as f of x with the limit a to b, so which is nothing but f of b minus f of e. So usually we put a modulus if we are talking about area, or else we can keep the sign whatever we get. So but area is always positive, and the negative area also has a significance that depends upon the question. Let me not comment much about it right now. So let us just understand the theorem as it is. Okay, so area function associated with the definite integral represents the net signed area between the graph of a function and the x-axis over the specified interval. The function is like this, and there's a x-axis, and we have a limit now a and b. So this is the area we are talking about. So this area of the given function between a and b with the x-axis, and y is equal to a, y is equal to b between the curve. So this is the region we are talking about. So that is what is expressed here. If there is a function like this, and we have a and b here, Okay, so we have x is equal to y is this is x is equal to a. Sorry for that. This is x is equal to a. This is x is equal to b. Right. So between this, we are getting the area. Okay. So area function is typically treated as a of x, which is always given by integral with only a to x f of x dx. Okay, so this is again symbolical way, so we just have to remember the theorem. We can use them in the application of integrals mainly. Okay, so let me erase this part again. So we have now under definite integrals again, we have second theorem. What does it say? Yes, so the theorem says let f be a continuous function on the closed interval a to b. What is in the closed interval? We are having a and b included in that. Let a of x be the area, then a of x is equal to a dash of x is equal to f of x to all x that belongs to this region. So this is the theorem. Okay, so just remember this theorem statement. Okay, so let's quickly check the next theorem. Second fundamental theorem of calculus. Okay, if there is a statement asked, we should be able to know that, and the application we're going to see later. And the theorem says now, if we have an integral of f of x dx from a to b, its value is going to be f of x from b to a, and that is by substituting the value of b minus a. What we get, that is our area. So let f be a continuous functions defined in the closed interval a comma b, and f be antiderivative of f, then we are having this. So just like the examples again, if we know the value, we can substitute and get the value of that as it is. Okay, yes. So we are coming to the end of this session by knowing area functions, fundamental theorem of integral calculus we have done. Okay, some properties of definite integrals. With this, I'm going to wind up. What is a property? These properties are going to help us in the solving definite integrals. So the first property is some key properties of definite integrals are listed below. Property one is if you change the variable of the integration, the value will not change. If it is variable of f, same function, if we have a variable t, this will not change anything. It's because we are going to resubstitute the variable by the limit. So x will become a, t will also become a and b. So that's why this will be same. The second property is very important, interesting, which will be helping us in many places. If we have an integral from a to b limit dx, if you want to change the direction, it will become change the sign also. This will be still same. Therefore, integral of f of x a to b is equal to minus integral of b to a, same function f of x. Okay, that is because if you substitute after integrating, it is f of a minus f of b minus f of a, whereas the opposite one is f of a minus f of b. It is only changed by the sign because of the direction. That is why when you change the sign, you can change the direction of the integral limits or vice versa. Okay. Yes. So now we have next theorem, our next property. Please pay attention to these properties. So if you want to have a limit, say a to b f of x, and between a and b, if there is a number, if there is another number c, such that they are continuous in these places, then we can split this as a to c f of x dx plus c to b f of x dx. These are all going to be useful for us in solving the definite integrals. Okay, so if there's a number between them. Okay, the last one, if you have integral a to b f of x dx, okay, and that will be always equal to a plus b minus x dx. Okay, that is because you can just substitute that a plus b minus x in terms of t. We end up with, we change the, when the value of the variable changes, limit also changes. So when you put a plus b minus x is equal to t, what happens is, when you differentiate, dx becomes dt. Okay, so yeah, so please check all these things. Dx become dt, and x becomes a, t becomes b. Okay, when x becomes b, t becomes a. So that is how this is again changed to minus of integral of a to b uh, f of t and dt. So please check these statements clearly. We are going to use it in the next class. Definitely we are going to use it in application of integrals. These properties are very important for us. Okay, and also we are going to solve some other questions in the definite integrals using this. The last one is integral of 0 to a f of x into dx is equal to a to 0 f of a minus t into dt. Okay, so which is also equal to this 0 to a. We can change the direction, 0 to a f of a minus t dt. All that is same. Okay, so these values are all same. So try to understand and remember them. Last function, last property, if you have a limit like 0 to 2a, okay, we can split as 0 to a f of x dx plus again 0 to a f of x dx. So we can split that. Okay, so we can also write it like this: 0 to 2 a f of x dx can be written as 0 to a f of x dx plus 0 to a 2a minus x dx. So please try to remember these theorems. Okay, so we have another function, another theorem, which is 0 to 2a f of x dx can be written as 0 to a f of x dx plus 0 to a 2a minus x, which is coming from the previous function. Okay, so I'm just taking a quick review of all these functions. Okay, so now, yes, so if there is a limit with the negative numbers and the positive numbers on the lower and the upper limit, f of x dx can become 2 to root of 0 to a f of x dx if f of x is what? Is an even function. Very good. Okay, so and this will become minus a to a plus 0 to a. In that case, what is even function? That's the next question. So what is even function? Even function is nothing but a function after substituting the negative value, the function is not changing. F of minus x is still f of x. Such a function is called even function. So please go through all these theorems in your textbook